So welcome back. So Units 1 and Units 2 were all really about setting the stage so that we can roll up our sleeves and do some real semiconductor work. So that's what we're ready to do. That's what we've been discussing in Unit 3, talking about how we compute the electron and hole concentrations, which are so important to the operation of a semiconductor device. So let's just summarize the learning objectives in this unit. We began with the Fermi function. We did not derive it, but you should understand what it is, how it is used, and what the effect of moving the Fermi level or increasing the temperature is on it, what it means. You should also understand how the location of the Fermi level controls the concentration of electrons and holes. You should be able to relate the intrinsic carrier density to the effective densities of states for the semiconductor, the conduction band and the valence band, and to the band gap of the semiconductor. And you should know what the effective density of states is and how it differs from the density of states. Finally, you should understand how you relate the location of the Fermi level relative to the conduction and valence band edges to the carrier densities, or relative to the intrinsic level and what the intrinsic level is. And finally, you should understand how you can compute the carrier densities at a given temperature, from low temperature, moderate temperatures, to high temperatures. Well, this is our Fermi function. It gives the probability that a state in equilibrium is occupied, so it's a number between 0 and 1. And there are two parameters in this function, the Fermi level, or the Fermi energy, and the temperature. This is a plot of the Fermi function. It's a probability a state is occupied. It goes from 1 to 0 at very high energies. If you look at the Fermi energy, one of the parameters in this, you can see that at the Fermi energy, the probability that a state is occupied, if such a state does indeed exist, the probability is 1/2. The transition from probability 1 to probability 0 occurs over a temperature range of a few kT. As we go to energies that are much below the Fermi energy, the probability that the state is occupied approaches 1. As we go to energies that are much above the Fermi energy, the probability that the state is occupied approaches 0. Okay, temperature is also very important. Here's our Fermi function again. There's our Fermi level again. It has probability of being occupied of 1/2. Now, what if we change the temperature? We're going to change the width of this transition region. If we increase the temperature, the width, the transition, the energy range it takes to transition from probability 1 to probability 0 becomes much wider. And as we go to lower temperatures, it becomes much narrower. As we go to t equals 0, this becomes a step function. At t equals 0, all states below the Fermi level are occupied, all states above the Fermi level are empty. Well, using this concept of Fermi level and the fact that it gives us the probability that a state is occupied, we can find out how the states are distributed, or how the electrons are distributed within the conduction band, or holes within the valence band. And we'll find an answer like this. The number of electrons, the density of electrons in a small energy range is just equal to the number of states in that small energy range times the probability that the states in that energy range are occupied. That's given by the Fermi function. And we showed by a simple calculation that the peak of that probability occurs very close to the bottom of the conduction band, 1/2 kT, which is a very small number. So electrons in the conduction band sit very close to the bottom of the conduction band. We could do the same thing for holes in the valence band, and we would find that the holes are very close to the top of the valence band. So, important point to remember is that in equilibrium and near equilibrium, unless we work very hard, the electrons and holes are going to be very near the band edges. That's what we'll assume basically for the remainder of this course. Okay, now that we know how the electrons are distributed in energy within the conduction band, same thing for holes, how the holes are distributed in energy in the valence band, we can simply integrate over the conduction band and find the total number of electrons that are in the conduction band. So we simply have to do this integration. We know the Fermi function. We know the density of states. We simply do the integral. When we do the integral, we find that the equilibrium electron concentration is a set of constants, n sub c, times a function that we call the Fermi-Dirac integral of order 1/2. So that's a complicated function. Analytical expressions don't exist for this particular order of Fermi-Dirac integral, but that's what the answer is. And you can see that it's a function of the location of the Fermi level with respect to the bottom of the conduction band. If we were talking about 2d electrons or 1d electrons, we would get different answers because they have different densities of states. Now, this quantity n sub c, we call this the effective density of states. Not the density of states. The density of states tells us how the states are distributed in energy. The effective density of the states is the result of integrating all of those states and is given by this expression. So it's sort of important to file away that in 3D it varies as the mass to the 3/2 power and as to the temperature to the 3/2 power. Well, what is this quantity m sub d star? This is known as a density of states effective mass. It's not an actual effective mass. It's not related to the curvature of the bands as we discussed earlier, but it's some combination of effective masses. So for example, silicon is an ellipsoidal band semiconductor. It has different effective masses along and transverse to the major axis of the ellipsoid. Which effective mass do we use? Well, if we solve this problem, we use some combination of effective masses for a semiconductor like that. We also have to account for the fact that there are 6 valleys in silicon. If you wrap all of that together, we can put it together in some quantity that we call the density of states effective mass. So it allows us to use this simple expression if we use the appropriate combinations of masses for the particular semiconductor. Oftentimes for simple semiconductors, it's just a simple band curvature near k equals 0. Well, this Fermi-Dirac integral is a little complicated function. It depends on the Fermi level. We often plot the Fermi level in reduced terms, dimensionless terms. A to F is the location of the Fermi level with respect to the bottom of the conduction band in units of kT. And if we do a plot, we'll get something like this. Now you remember that if the Fermi level is well below the bottom of the conduction band, things simplify. We have a non-degenerate semiconductor. In that case, the Fermi-Dirac integral simplifies and simply becomes an exponential. That's much easier to work with, much easier to do calculations with. We don't need some special numerical integration to find what the answer is. So in that case, if we were to plot log of the Fermi-Dirac integral versus A to F, we would simply get a straight line. That's the non-degenerate approximation, the exponential approximation to the Fermi-Dirac integral. When the Fermi level is above the bottom of the conduction band, you can see we get increasing amounts of error, and you can see that the Fermi-Dirac integral is always smaller than the exponential approximation, is equal to or smaller. Well, that brings in this concept of non-degenerate semiconductors. As long as the Fermi level does not get too close to the band edges, we can use these exponential approximations. That's where most semiconductor engineering is done. We'll get answers that are either accurate. Sometimes we use those simplified exponential solutions even when the Fermi level gets too close to the conduction band or too close to the top of the valence band. We know we're making some error. We know we'll get qualitatively the right answers. We know that if we need the actual precise numerical answer, we can take the time to compute a Fermi-Dirac integral. But most semiconductor thinking and discussion is done with these non-degenerate expressions. So it's the non-degenerate exponential expressions that you will mostly see for the remainder of this course. Now, it's not surprising then that we have very simple expressions for how we relate the electron concentration to the Fermi level. So the way to remember the order in which these the Fermi level and the bottom of the conduction band occur is that the higher the Fermi level is, the higher the probability that states in the conduction band are occupied, the more electrons there will be in the conduction band. So we have an exponential that goes as EF minus EC over KT. Just the opposite for holes. The lower the Fermi level is, the higher the probability that we'll have empty states in the valence band, so the higher the hole density is. These are very simple expressions that we will use over and over again. Now we can take those two expressions, we can multiply them together. The Fermi level drops out when we do that, and we get an expression for this intrinsic carrier density that we've talked about before. We can see it's independent of the Fermi level. Remember, we're assuming a non-degenerate semiconductor. That's not the case when the semiconductor becomes degenerate. It depends exponentially on band gap, gets very small for wide band gap semiconductors. It depends exponentially on temperature. It can get very large at high temperatures. And remember, for silicon at room temperature, Ni just happens to have a very convenient number. It's very close to 1 times 10 to the 10th per cubic centimeter. Well, that brings in this concept called the intrinsic Fermi level or the intrinsic level. So the electron density is related to the Fermi level by this standard expression. If we locate the Fermi level at a location we call the intrinsic level or the intrinsic Fermi level, then the electron density will be equal to its intrinsic density. And we can solve for the location of that intrinsic level. We'll get this expression. EC plus EV divided by 2 is right smack in the middle of the band gap. But the effective mass for electrons and the effective mass for holes is slightly different. So to get the hole concentration equal to the electron concentration equal to the intrinsic concentration, the Fermi level is not exactly at the middle of the band gap, but it's very close. So this is the expression for the intrinsic level, which when we're sketching energy band diagrams, we'll just sketch as a dashed line in the middle of the band gap. So to summarize, we have these simple expressions for a non-degenerate semiconductor which relate the location of the Fermi level to the carrier concentration. We can either relate the location of the Fermi level to the corresponding band edge, conduction band minima or valence band maxima, or we can relate the electron concentration to the location of the Fermi level relative to the intrinsic level. Is the Fermi level above or below the intrinsic level? These are mathematically equivalent and identical. We'll use the one that is most convenient for us. We have these effective densities of states, which we'll need whenever we're doing a calculation. We have this expression for the intrinsic carrier density, which gives us an understanding of how it varies with band gap and temperature. And remember, in equilibrium, N times P is always Ni squared. So if we have an energy band diagram and we see the Fermi level above the middle of the band gap, above the intrinsic level, we know there are more electrons than holes. And as it gets more and more above the intrinsic level, closer and closer to the conduction band minima, we get more and more electrons. If we see the Fermi level below the intrinsic level, we know we have more holes than electrons. So we can quickly glance at an energy band diagram and deduce whether this is a p-type semiconductor or an n-type semiconductor that we are talking about. Now, it was very important. What we're leading up here is the way we produce desired electron and hole concentrations in a semiconductor is largely by doping the semiconductor. And we talked about how do we compute, given a doping density, how do we compute that? Well, we began by thinking that we have a uniform slab of semiconductor. We have n-type dopants, perhaps we have p-type dopants also. We have mobile holes that are positively charged. We have mobile electrons that are negatively charged. At any finite temperature, some fraction, maybe all of those dopants are ionized and they're charged as well. Well, overall, the mobile charges are going to move around and cancel. Positive charges will cancel negative charges, and we expect overall to have a neutral semiconductor after that process occurs. So that's called space charge neutrality. Generally, it's a good assumption in a uniform semiconductor. We also know that the product of N and P is equal to Ni squared in equilibrium. Well, we can put these two equations together. In an N-type semiconductor, we have two equations and two unknowns. We could solve for the electron concentration. We will be solving a quadratic equation. We get this expression. If we want the hole concentration, we just use Np is equal to Ni squared. If we have a p-type semiconductor, we eliminate the electron concentration in this first equation, and we solve for the hole concentration. Again, we solve a quadratic equation, we get the hole density. If we want the electron density, we use Np is equal to Ni squared. So these are really the expressions that we should be using in general. Now, if we're lucky, and we're in what we call the extrinsic region, where the properties of the semiconductor are determined extrinsically by these dopants that we have introduced into the pure silicon lattice. When the net doping density is much bigger than the intrinsic density, we can simplify those quadratic equations and we get a very simple answer. The electron concentration is equal to the net donor density in an N-type material, and then we get the hole concentration from Np is equal to Ni squared. Or if we have a p-type material, the hole concentration is equal to the net acceptor concentration, and the small electron density is determined by Np is equal to Ni squared. This is the region that we are most often operating in widely used semiconductors like silicon. Now, that's the extrinsic region. What if we crank the temperature way up? Then we know that the intrinsic carrier density becomes much larger. We have to use that full quadratic equation. Eventually, the intrinsic carrier concentration dominates, and then N is equal to P is equal to Ni. That's what we call the intrinsic region when we go to high temperatures. What if we go to low temperatures? Okay, low temperatures, the dopants start to freeze out. So we have fewer and fewer carriers. Eventually, if we go to low enough temperatures, all of the dopants will freeze out, and we have no electrons in the conduction band or no holes in the valence band. This is called the freeze-out regime. So if you look at that regime, as we start increasing the temperature and moving electrons from the donors into the conduction band, the concentration is proportional to E to the conduction band energy minus the donor level energy, which is just a little below the conduction band, remember? That should look familiar to you. It's sort of like the donor levels are acting as the valence band, and the conduction band is acting as the conduction band. That looks similar to the expression we had for the intrinsic carrier concentration. Okay, so it's a little more complicated to do these calculations in the freeze-out regime, but they can be done. Qualitatively, it's easy to understand. Now, finally, we want to understand how the Fermi level varies with temperature. So, given that we can compute the carrier concentration at any temperature, we know how the carrier concentration is related to Fermi level, so we can compute the Fermi level at any temperature. If we were to look at how the Fermi level in an N-type semiconductor varies with temperature, we would get a plot that looks like this. At very low temperatures, the Fermi level has to be above the donor level, because all those donor levels are occupied. Those fifth electrons are sitting on the donors. But as we increase the temperature and go to higher and higher temperatures, eventually we're dominated by the intrinsic carriers, and when the semiconductor is intrinsic, the Fermi level is at the intrinsic level, which is almost exactly at the middle of the band gap. So we'll expect that versus temperature, the Fermi level in an N-type semiconductor would have a variation that looks like this. Similarly, for holes, we can deduce that the variation would look like this. You should understand these plots, where they come from, and at least qualitatively how they are sketched. So let's summarize. These are the learning outcomes. Be sure that you understand the Fermi function, what it is and how it is used, and how changing the location of the Fermi level and the temperature change the Fermi function. Understand the relation between the Fermi level and the equilibrium carrier densities and what we mean by non-degenerate and degenerate semiconductors. Understand how the intrinsic carrier density is related to band gap, to effective density of the states. Understand what the intrinsic level or the intrinsic Fermi level means. You should be able to relate the equilibrium carrier densities to the location of the Fermi level relative to either the band edges or to the intrinsic level. And finally, you should understand how we compute, given a doping density, how we compute the electron and hole concentrations versus temperature. If you understand those concepts, you're prepared to move on into Unit 4, in which we will, for the first time, move out of equilibrium and ask what happens to a semiconductor when we leave equilibrium conditions.